Welcome to the video lesson on section 5.1. In this lesson, our target is to learn how to be able to estimate distance traveled when we're given a velocity function. That velocity function would either be given as a table or a graph in this section. All right, so we're going to start off with just a basic formula that distance equals velocity times time. You might have memorized that, at an earlier time as rate times time. Of course, we all understand that velocity is a rate. So for instance, if we look at this first problem here, we've got 30 miles per hour, which we could write as 30 miles per hour like this. And if we multiply that by 4 hours, you'll notice that the hours cancel, and our unit that we're left with is miles. So that ends up equaling 120 miles. And so we did exactly what the formula up here said we should do. We took the velocity. This is our velocity. We took it times our time, 4 hours, and when we were done and the units canceled out, we saw that we did get the distance traveled. Now, on this next one, we're going to take a look at this and we're going to see how we can use a little geometry to show this. So this first one, I've got, I'm going 12 feet per second for 3 seconds, and we're going to actually draw a rectangle to show this. So on the base here, this width is 3 seconds, and the height of my rectangle is going to be 12 feet per second. Now if we multiply those, we're going to see that we get area, and our area ends up being 36 feet. We can do the same thing for the next one. This time we're going 5 seconds, so this is going to be a little wider. And our speed is a little slower. We're going 8 feet per second, and so we've got this other rectangle at 8 feet per second. And when we multiply these, we get 40 feet. And the area of the rectangle becomes the distance traveled. And that's going to be really important for what we're doing. So area of the rectangle equals the distance traveled. And in this case, we've got two different rectangles, and we simply add up the areas to find the total distance traveled, which is going to give us 76 feet for the total distance traveled. All right, so let's jump in. This is more like what our calculus problems are going to look like. We're either given a table or a graph, or in this case we're given both, and we're asked how far did this car travel in 10 seconds. And you'll notice over here there's all kinds of rectangles drawn over here, and we're going to start off with these lower rectangles. So we're going to start off with this very first one, and I'm going to do this in blue. And you'll notice that the width of this rectangle is 2, which is the same thing as the difference between these two right here. So from 0 to 2, my time is 2 seconds, and during that time, I'm using a height of 20, which is the left-hand side. And what we're going to call this is the left-hand sum. So LHS equals the left-hand sum. And we're going to notice that we have 5 rectangles here. 1, 2, 3, 4, 5. And we can see that from the table in that if we look at each pair, and we notice the width of each one is 2. And we're going to, for each of them, take the left-hand velocity. So in this first one, we're going to take a width of 2 times a height of 20, and we've done the first rectangle. When we take the next rectangle, which is this one in blue, we also have a width of 2, and we have a height of 30. And notice that 30 comes into play right there. Our next rectangle also has a width of 2, and we're going to use the height of 38, and that's this one right here. Followed by the one with a width of 2 and a height of 44. So that's this one. And on here it's here. And then the last one, a width of 2 and a height of 48. Now you'll notice when we do our left-hand sum, we do not use that last value. And then we could actually factor out that 2. So 2 times 20 plus 30 plus 38 plus 44 plus 48. And that answer comes out to be 122. I also want us to notice that this is an underestimate because you'll notice all the rectangles are below the curve. Now, if we can do a left-hand sum, we can also do a right-hand sum. So we're going to start this over. I'm going to get rid of all my blue markings. And this time we're going to go with some red markings. So this time we're going to do our right-hand sum. And just like in the left-hand sum, every width is 2. So they're all 2, 2, 2, and 2. And since I know that's going to happen, I'm actually going to factor out the 2 right away. And then I want the height of each one. Now you'll notice the right-hand sum is above the curve like this. So here's my first rectangle, and I'm going to use the height on the right. So I'm going to do 30. And then as I take all of these, you'll notice I did not use that first one. I'm going to use all the other heights. So that one's height of 38. This one right here, oops, I'm up to the height of 44. This next one has a height of 48. And my last red rectangle, this one here, has a height of 50. And when I work out the math on that, that's going to be 162. And clearly the rectangles are above the curve, so that's going to be an overestimate. All right. So you might ask yourself, well, how do we get a better estimate? Because clearly all we managed to do was say it was between 122 and 162. And we can certainly average those. So that's one way, although we're not guaranteed that the actual value is right in between. So how do we get a better estimate? Well, with more rectangles. So with more rectangles, we eventually, as they get skinnier and skinnier and skinnier, and you should be thinking limits here, so the limit as the width of the rectangle goes to 0, we get a nice smooth curve, and once we get a nice smooth curve, this one gives us the exact distance traveled. So right now I want to make sure that we understand that the area under the curve, so, and by the way, this is for a positive. So for a positive velocity graph, so one that does not go below the x-axis. So for a positive velocity graph, area under the curve, area under the curve, and when we say area under the curve, we mean down to the x-axis, not below the x-axis. So area under the curve is the distance traveled. This is a huge thing to have figured out. And if you've been taking physics this year, you already know that. So this area underneath a velocity graph represents the distance traveled. Now sometimes we're going to get problems like this, where it asks us to find the total distance traveled. And what they want you to understand is what's said right here. Shaded area represents the distance traveled, which means all I have to do is use a geometry formula because this is a lovely triangle. So I'm like, well, I know the area of that. Area equals distance traveled. Okay, that's great. And I also know that area, in this case, is simply 1/2 base times height. And I can clearly see the base is 3 because it says so right here. So my distance here is 3. And I have a lovely formula to find my y value. So my height is going to be 5 times 3, which is 15. And there we go. We've answered our question, 45 over 2, or 22.5 feet. I also want to point out that our units help us out here. We can do 1/2. This was 3 seconds. This was 15 feet per second. And you'll notice the seconds cancel and our answer is in feet. All right, we also want to make sure we understand the difference between these two terms, the total distance traveled and our change in position. So I want you to look at this first one. If I go 20 feet per second for 10 seconds, I should note that I'm going 200 feet. And here I've got -5 feet per second for 2 seconds. Well, that comes out to 10 feet, but that's 10 feet to the left. And 200 feet, that was to the right because it was positive. Now, if I want total distance traveled, well, I went 200 feet to the right, and then I went 10 feet to the left. Well, the total distance I traveled was 210 feet. But my change in position is this distance right here. I started here and it ended up here. And so this is my change in position, which is only 190 feet to the right. Change in position is also sometimes called displacement. You'll hear that term more as we progress. All right, so this is going to look a lot more like what a lot of your homework problems will look like. We're given a chart, t and f of t, and we're going to be asked to find the left-hand sum and the right-hand sum for this particular graph. So when we're told that n equals 4, now I want you to understand when it says n equals 4, we're talking about 4 subintervals. And if we're talking about 4 subintervals, we're talking about 4 rectangles. When I have a chart, it kind of helps to show the rectangles like this. So here's 1, 2, 3, and 4. And I can see the distance between each of these is 2. So my width is 2. And my width is delta t, which in this case equals 2. Now I found 2 in this case by just looking at the chart and drawing out my 4 and seeing the difference. There is also a formula I can use, and that is delta t equals my maximum minus my minimum divided by the number of subintervals. So I could take 23 minus 15 and divide it by n, which is 4, and that would also get me to 2. So I now know my width is 2, and now left-hand sums, remember I'm going to use the left-hand heights. So I'm going to use the 4 heights to the left. 10 plus 13 plus 18 plus 20. Whereas on the right-hand sum, I'll just switch my colors here, my width is still 2, but I'm going to use the right ones. So 1, 2, 3, 4, I'm going to use those 4. 13 plus 18 plus 20 plus 30. And then I've got some answers here for these. Let's see. Our right-hand sum comes out to 162, and our left-hand sum was 122. And I'm just realizing I looked at the wrong side for the numbers on that previous slide. So I'm going to just go back here and fix this up. This was not 122 and 162. This actually was 360 and 420. Sorry about that. All right, so carrying on, 122 and 162, and here we have an underestimate, and over here we have an overestimate. And we know that because when we were doing the left hand, we were using all the smaller numbers. So on each interval, I was using the smaller of the two numbers. And on the right hand, I was always using the higher of the two numbers. Now, we could do the same one with a little less work with just 2 intervals. And so we said, what if n equals 2? That means 2 rectangles. Now remember, I can figure out delta t 2 ways. I can say, okay, if I have 2 rectangles, it's going to look like that. And I can see my width is 4 and 4. Or I can do that formula again. So 23 minus 15 divided by 4, which gives me 8 over 4 or 2. All right. Oops. Take that back. N is 2, not 4. So I'm dividing by 2, 8 over 2, which is 4. So delta t equals 4, which means my width is 4 on each of these. And so my heights on the left hand, now I'm looking at the left hand of this region. So see how I drew this rectangle? I'm going to use the 10 for the first rectangle. And for the second rectangle, I start here. The left hand is right here, which is 18. And so when I do that, and I've got, let's see, 112 for that one. On the next one, for the right-hand sum, my width is still 4, but I'm going to use the right hand. So on this first rectangle that goes from here to here, the right-hand height is 18. And on the second one, the right-hand height is 30. And so there I get 192. All right, so in our next slide, it asks if in all our examples, our left hand was an underestimate and our right hand was an overestimate. We're asked if that's always the case, and the answer is no. It really has to do with what kind of graph you have. So up till now, our graphs have all been increasing. So for instance, if we looked at our first graph, I think it had this kind of shape. It was increasing. And if I take my left hand, it's always underneath. So I go up to the curve and draw a rectangle. It's always underneath. But if I had a decreasing graph, maybe something like this, and I did my left hand, you would know that, oh look, it's above the curve. So we should note that in an increasing graph, so increasing graph, the left-hand sum is an underestimate, but in a decreasing graph, it's the opposite. So if it's a decreasing graph, the left-hand sum is an overestimate. And I want to point out again that we're only dealing with positive graphs. So I should say an increasing positive graph and a decreasing positive graph. All right, the last thing I want to do here is talk about all the formulas in general. So in general, I could have some function, and listed above across the top are a whole bunch of times, starting at t sub 0 and ending at t sub n. And here are all the heights of my function, starting at f of t sub 0 all the way to f of t sub n. Whenever we reference n, that is the number of rectangles. So n equals the number of intervals. So the number of intervals, or, oops, or the number of rectangles, same thing. Whenever we ask for delta t, our formula is b minus a all over n, where b is this value and a is this value. So we could also say t sub n minus t sub 0 all over n would be another way to say that. For our left-hand sum, our width is delta t, and then we take all the left-hand y values. So that's going to be f of t sub 0 plus f of t sub 1 plus f of t sub 2, and this goes all the way on to the one before the last, so f of t sub n minus 1. On the left hand, we don't use that value, and so the last one we're going to use is t sub n minus 1. Now with the right-hand sum, our width is still delta t, but we're not going to start at this one, so this time we'll get rid of that left one, and there we go. We've got f of t sub 1 plus f of t sub 2 plus f of t sub 3, and our last one is f of t sub n. And that's it. Our homework is assignment number 1 on that next assignment sheet, and it's right here. Section 5.1, 1 through 9 odd, 15, 17 through 20, and 21 through 25.